Okay, problem 5 is basically asking us to prove exactly the same thing. So these qualities of sets that we had on problem 4, but instead of using Venn diagrams, which are limited because they only work for up to 3 sets, to use logic to prove it. I abbreviated the statement by just saying that verify logically. This is very vague, but I just didn't want to copy the whole statement. So how to use logic to prove that these 2 sets are the same? So remember, 2 sets are the same if they have exactly the same elements. So the idea is, if these two sets are the same, if and only if the statement that X belongs to the first is logically equivalent to the statement X belongs to the second set. Okay? So that's the translation from sets to logic. Okay? So this equality of sets in here is the same as to say that X belongs to the first is logically equivalent to that X belongs to the second. So that's the approach that we take. Okay? So I write this statement X belongs to the first set. So X belongs to A minus A inter B. Okay? Now, what does it mean to be in a difference of sets? So we have a definition. And the definition for an element to belong to a difference is that X belongs to the first set and X does not belong, or sorry, what I was writing is right, but I want to write it in terms of the logical symbols that we're familiar. So, and not belong to the second set. So it belongs to a difference if it does belong to the first, but does not belong to the second. Okay? So this is definition of difference of sets. Similarly, I can use the definition of intersection to translate these in terms of logic statements again. So let me just copy the first part and let me interpret what does it mean to belong to an intersection. It means that X belongs to the first and X belongs to the second. Right? It belongs to both. Notice that the notation here is also convenient because the intersection turns into an and. And as we will see in the next part, the union translates into an or. So the notation again is convenient. Okay? So in these 2 steps, I wrote what it means to be in a difference and what it means to be in an intersection. And notice that I have everything now in terms of 2 statements. X is in A and X is in B. So I have a logical statement in here with some operations, but depending on only 2 statements. X is in A and X is in B. Now what I want to do is manipulate this expression or simplify it and see if I can get that X is in that difference A minus B. So in this part in here is just Boolean algebra, okay? You just manipulate these formulas. So in here, for instance, you can see the Morgan's law shouting at you, right? So we have this not with an and in here, we can use the Morgan's law. So let me do that. So I copy the first part, and the Morgan's law is going to give me the negation of the first. The and becomes an or, and I have a negation of the second. So, De Morgan's law. Now, what can I do? Here I have and here I have or. And I can use distributive law. So I can distribute these, and what do I get? So I have x belongs to A and not x belongs to A. And here I have connecting is or. I have x belongs to A again and not x belongs to B. Okay, distributive law. Now, what happens? Here I have x in A and not x in A. So, remember, this is a contradiction, because it cannot be true at the same time that x in A and x is not. So this is contradiction. So it's a constant equal to false. And you have false or some expression, then you have just the expressions, right? So it's one of the rules, contradiction or something is something. So this is logically equivalent to just the second one. X in A and not x in B. But this is exactly the definition of x being in the difference A minus B. So that's logical equivalent of x in A minus B. So we've done what we were set out to do. We proved that an element belonging to the first set is logically equivalent to the same element to belong to the other set. That means that they have exactly the same elements and therefore the sets are equal. Okay? So this is part A. Now, part B is actually a little bit simpler, although it looks more complicated. So, the idea of how to do it is very similar. The idea is exactly the same. We start by saying x belongs to the first set, so A union quantity B inter C. And then we start interpreting what it means to be in the union, and then what it means to be in intersection. So, by definition, to be in a union it means that it is in the first or it is in the second. Now, the second is an intersection, so we have to interpret or use the definition of what it means to be in an intersection. So I copy the first and interpret the second. The second gives me x is in B and x is in C. So again, you notice how union becomes an or, intersection becomes an and. And what can I do now? Well, I have different operations. I can use the distributive law, and these would give me x in A or x in B, and x in A or x in C. Now, what does it mean to say that x is in A or x is in B? Well, that is the same as to say that x is in the intersection by the definition of intersection. So this first is equivalent to x belongs to A union B. And here I have x in a very similar manner, right? Again, is an or, x in A or x in C. That is exactly the definition of x belonging to the union of A with C. So I have these. Now, I have x in some set and x in some other set. What does that mean? By definition, this means that x belongs to the intersection of the first with the second. So A union B intersect with A union C. And we're done. Again, as you can see, I started with an expression that said x belongs to the left-hand side, and through logical equivalences, I got that x belongs to the second set. Okay? Now, again, this is similar to algebra. And whenever sometimes you want to prove the two things are equal in usual algebra, sometimes what you do some manipulation with the first, some manipulation of the second, and then you see that after manipulations they become the same, right? And sometimes this is useful to do in these situations, or with Boolean algebra. You can write, expand all the definitions of what it means to be in the first set. So that would be to come to this point in here. Okay? So you can just interpret what it means to be in unions intersections. So you would get to here. And then stopping here, you interpret everything that you could. You simplified, so to speak. You changed to logic everything that you could. And then you could look at what it means to be in the second set. Basically, what you do, if you look carefully, would be to go from here to here to here. Okay? So by simplifying these two expressions, so to speak, the first one would come from the first to here, from the first line to the third, and then simplifying the second expression, you'd go from the bottom line to the fourth line. And you'd be left with wondering whether or not these two would be logically equivalent. And you could just realize at this point, by staring at these two, that you want them to be logically equivalent, and see if there is some logical steps, some Boolean algebra that you could do in here to get the equivalency. Of course, in this case, if you looked at both, hopefully you would just jump, in front of your eyes in there. So this is just distributive law. Okay, so that's one way that sometimes you can do it. Of course, whenever you actually write in your solution, you write it cleanly, right? So you connect everything in one direction here. But the process of actually getting this to work can be done as I just described, by writing down what you have in both sides in terms of logic, and then whenever only have logical statements, no unions, no intersections, no differences, you can sort of try to connect them together with logical arguments. The same thing could go from this one in here too. The interpretation of the first one would stop in here, right? So there's no unions or intersections or differences anymore. The interpretation of the second is just this. And so you'd be left with a problem of showing that this third line in here is logically equivalent to this one in here. But it becomes just a logic problem, and you can try to manipulate the symbols so that you see that they're the same. Okay, so you can see if you can simplify this one all the way through this one. And one last remark before we move on. What you see here is a distributive law for sets. So you can see a distributive which is coming straight from the logic version of the distributive law. Right? You have mixed operations, it just distributes. And I think in one of your homework problems you're going to do the other distributive law. Okay, so it's going to be very similar to these, but what you just proved in here is a distributive law for unions with intersections. Okay, all right, so that is it for this problem 5.